Let's talk about mixed models. We mentioned that a little bit previously when we were talking about analysis of variance. So let's talk about proc mixed in general. First of all, it's not as hard as it looks. Mixed models, that is. That's actually George Harris throwing somebody, I think, in the Olympics. That was probably just as hard as it looked. So mixed models aren't nearly as complicated as some people make them sound. If you're familiar with PROC-GLM, the general linear model for SAS, proc mix should be pretty simple to pick up. In fact, when I first heard about this brand new statistical procedure, I had really geared myself up for this long stretch of reading documentation, figuring it out. Because at the time I was the senior statistical consultant at a major research university and I was supposed to know these things, right? So I was pleasantly surprised when I found out that mixed models were not nearly as new and amazing as I'd expected. A little disappointed, but surprised. So in a nutshell, first of all, in the vast majority of cases, a mixed model and a general linear model will give you the same results. If you don't know, now you know that both ANOVA and regression are specific cases of the general linear model. Now, if you aren't familiar with GLM, that previous statement was of no help to you whatsoever. So let's start with a few basic things. GLM, if you just see that PROC-GLM and you don't know what it is, PROC-GLM is the general linear model, both general and linear, also a model, assumes a few things, one of which is that your dependent variable is continuous, and we will talk about those assumptions shortly. Mixed and GLM both are used to predict the values of a numeric dependent variable. Both of them assume that the dependent variable is normally distributed. Now, in many cases, GLM may be identical to proc mixed. In fact, if you only have fixed effects in your model, they are exactly like GLM. And I will explain why. A mixed model includes a mix of fixed effects and random effects. So that's the key to understanding the whole thing. If you don't know what a fixed or a random effect is, you will very, very, very shortly. So according to SAS, the fixed effects parameters are associated with known explanatory variables, as in the standard linear model. Fixed effects can be either qualitative, like in ANOVA, or quantitative, as in regression. So maybe that still doesn't help. Let's give an example. Gender is a fixed effect. You can get all the genders there are. So if you have male and female, you have two genders. If you want to include a third gender, say people who are transgender, you can do that too. But the point is, you haven't randomly gone out and sampled genders. If somebody else wants to replicate your study, they can go and get people who are male and female. They're not taking a random sample of levels of the population. So it's often said that a fixed effect occurs when you have the complete population of levels of the explanatory variable. Now, let's look at a random effect. Schools are a random effect. So if I'm interested in the difference in, say, how secure students feel by school, I can go out and I can select a random sample of 17 schools. But that's not all of the schools that there are. So I could say there's variance among schools, but I've randomly got people within school who are going to be correlated. Now, if I go out and I get people from two different genders, probably the scores of the women are not that related to one another. They might be different from the scores of men, but the scores of, if I go out and I get Mary Lou Who and I get Cindy Jean someone else, I probably am not going to have a correlation between those scores within that group. Age, you might say, well, if I go and I get age, that's a random effect, right? Wrong. Because again, if you go out and you get kids of 8 years old and kids of 9 years old, the correlations of the ages within that group are probably 0. Let's say instead, let's give an example of a random effect. Let's say we have a new species. I made this up, the pine tree human hybrid. So we're trying to predict height, and we have gender, family, and age as variables. So if one of the variables is family, if you overpredict the height for one subject who's say 8 months old, are you more or less likely to overpredict the height for another subject who's 8 months old? And the answer to that is there's no relationship with your probability of correct prediction, because those 8 months old or 8 years old or however old they are kids, their scores are uncorrelated with one another. That is not true if you have people within the same family. I'm kind of short. Most of the people in my family are pretty short. There tends to be a correlation within family. So if you underpredict the height of one person in the same family, your equation is likely to underpredict the height of other people in that family. So there's going to be correlated errors. Now, that's the big difference between fixed effects models and random effects models, is that the fixed effects models account for correlated error. Now, one reason that mixed may not matter very much at all is that it may be there really isn't very much covariance within schools or sites. It might sound like there will be, it might sound logical, but it may turn out that when you do your actual analysis that there isn't much covariance. And so in that case, the mixed isn't going to really help you that much at all. It won't hurt. And I happen to have an example handy like that. I tested students at 3 different schools in 2 districts that happen to vary in resources and academic achievement. And that sounds just like an example for PROC mixed. I've got cluster sampling. It is not everybody's independently sampled. Students were sampled within school. We sampled schools within districts, and it turned out to have no effect at all. Both schools and districts are random effects. I have randomly sampled from the population of all schools, all districts, and you would think there'd be correlation within them, but when I ran the analyses, it didn't turn out that there was. Now let's talk about how mixed models really do differ though. Remember the regression equation? Y equals beta 1 plus, say, family income plus beta 2 times school plus beta 3 times IQ plus E. E is the error term. So that is the regression equation. Well, in a mixed model, we add another term to this. In the general linear model, the assumption is that the variables are IID. If you're not familiar with that term IID, you will hear it a lot in statistics. You see that notation a lot. IID stands for independent and identically distributed. So, for example, if I'm predicting achievement scores of students, I would expect that across the range of prediction, the variance of the errors would be the same. That is what we call homoscedasticity. So, the graph on the left shows what homoscedasticity looks like when you plot the errors against the predictor. For all the variables, for all the values of the predictor, the variance is approximately equal. And the graph on the right shows, again, that the variance around the predictor is about the same for all values of the predictor and the dependent. So here's my predictor times residual. You could see that this is random. You want to see random error. And you could see that the amount of error is the same across all levels of the dependent variable. So we're not having more error at the lower end or more error at the higher end. It's identically distributed. Isn't that good? GLM assumes errors are uncorrelated, homoscedastic, and normally distributed. In mixed models, errors are not assumed to be uncorrelated. So we don't say that the variables need to be normally distributed, notice, but generally we do assume that the errors are normally distributed. So we're equally likely to overpredict as underpredict. And the mean of our predicted value is going to be the actual value for the population. That's good, right? That's what we want. So yeah, that's it. I went through this whole thing to say that in GLM, errors are assumed to be uncorrelated, and in mixed, they're not. So here is how mixed models differ. You have y equals beta 1 plus family income, say, plus beta 2 times IQ, plus gamma times Z1. In this case, E is no longer assumed to be independent. So there can be, and usually are, a whole bunch of gamma effects. So one more thing to keep in mind, in the general model, we're trying to fit means. So the equation is modeling the means. So we think of this as we're predicting for person 1, person 2, and so on. But really, every person who has, say, a family income of 80,000 and goes to the best school and has an IQ of 120 gets the exact same predicted score, say an achievement test score of 650. So the mean predicted for the person with that profile is the same. We're trying to fit the means to a certain model. In the mixed model, in addition to means, we're trying to fit covariances. And we don't have to worry about that with the general linear model because we're assuming that all the observations are independent, and so thus by definition they have no covariance. So I'm going to talk about 2 more things and call it a night. And that is crossed versus nested factors. In mixed models, you'll need to specify if your data are nested. And nested factors don't mean your subjects have built themselves little houses out of twigs, but actually, eggs in a nest would be a perfect example of a nested model. Now, cross-factored, each level of each factor appears in every other level. So let's say you did a study, as I did before, it is very interesting, on marital status and employment. So you have people who are married and people who are not married and people who are employed and people who are unemployed, and you will have people that fit in all of those possible combinations. So you'll have married employed people, married unemployed people, single employed people, single unemployed people. That's a crossed factor. Nested factors, you have certain factors only within one group. So for example, if you have a pre and post test design with experimental and control group, usually what happens is subjects are nested within groups. So your subjects will either be in the experimental group or they'll be in the control group. You generally would not have the same subject in the experimental control group. You know, there are a lot of examples of that. Say, schools. However, I think that was a lot for today, so we're going to stop now and next time go through an example.